Sean Kolar, Gary Barrett, Aaron Lee, and Daniel Young. And our project is called the ExoRIS. This is it right here. Next slide. So what it is a powered assisted exoskeleton for the wrist, and it's designed for people who suffer from muscle weakness as a result of like stroke or muscle dystrophy, and they have a hard time performing everyday tasks. So what this does is it assists their wrist movement, adds extra strength in whichever direction they want to go. And it adds about 50 newtons of force, which is roughly like 12 pounds. So that's a substantial amount just for the wrist. Some features. Yeah, so it works from force sensors throughout the hand, linear actuators to provide the actuation. It has a OLED screen. It also has a low battery indicator and a warning system in case too much load is on the actuators. So we began by doing the free body diagram of the model. The key parts here are like the angle beta, which is the angle of the actuator on the arm. L2, which is the actuator itself, which extends and contracts. L1, which is the bar length to the hand. And then alpha, which is the angle of the wrist. So with that free body diagram, we came up with kinematic equations and simulated them in MATLAB. And these were the plots we got from that simulation, which basically just shows the angle of the wrist as the linear actuator extends out. So with this simulation, we got like a pretty good idea of what to expect. It helped us decide which linear actuator to get, like the length of it. And so we had a good idea of what type of range we would get in the wrist movements with this.
So to control whether our wrist moves up or down, or left or right, we had to use linear actuators. And to determine how far or how fast the linear actuators would move, we used 2 force sensors for each linear actuator. And we passed that through an op-amp, which then goes to the microcontroller through the ADC, and we calculate a value, and based on that value, we'll set a PWM and set certain pins on the H bridge to high. And the H bridge will then determine which actuators it goes to. And also, with mentioned earlier, we have some features as well, where if we have an overload on the actuators, then vibration mode will go off and it will be displayed on the OLED. And and also we have the battery sensing, battery monitoring, which also goes to the microcontroller, and we just take that value and calculate a percentage and display that as well.
So for the CAD designs of our exoskeleton, we essentially had 2 phases where we had our linear design, which is essentially a proof of concept to make sure that what we calculated in MATLAB actually works. And then we had our spring design, which we did this quarter, and it was essentially refining our design, fixing any problems that we had with it, and making sure it worked all that much better. So at first I said it was a proof of concept. We wanted to make the bar links, which controls the hand that's being directly connected to the linear actuator's rod. Make sure that it was a proper length so we get just as much angle as we expected. What we discovered from this first design is that it gave a great range of motion. It almost perfectly mimicked the MATLAB design. And With it, we just got a completely rigid design, but with it came problems such as it was extremely uncomfortable to wear because it was extremely blocky, it was too tall and could catch on objects. So what we did in spring was we essentially fixed all those and then added on to it. So we made it much sleeker, it's much more comfortable. Instead of being extremely blocky, it's smooth and fits around the arm and hand perfectly, essentially making it extremely comfortable. We also trying to make it more universal with Velcro, so you can tighten it to fit however you want. So it can almost fit anybody, but we're still going to make it completely universal. And essentially now it holds every component. It's completely mobile, as you can see John using it. It's got the battery, the PCB, the OLED, everything on one piece, so you don't have to be hooked up to a wall to work with it. It's used for everyday use. And the only problem with this design is we had to shorten the bar lengths because we had a lot less room to work with, but still got a decent range of motion for it to work perfect.
So our design of the electrical system began with obtaining a suitable power budget after we had all of our components chosen. So our power budget shown here, we have a 12-volt battery with a 3,000 milliamp hour life that's supplying the system. The 3.3 rail is supplied by a switching regulator. All the typical values are shown in parentheses with the max values outside. So based on these numbers, we were able to determine 3 ranges of battery life. So our typical value was 257 milliamp hours, giving us about 11 and a half hours battery life. And that's based on the assumption that the actuators will be moving roughly 40% of the time, having the other components such as the OLED, indication LED, and the micro running full time. Similarly, the max will be about 1.5 amps, will give us 2 hours, but that's worst case scenario, everything running full blast. And then we have a best case where one of the modes of operation, we can have our actuators lock in place. And if you wanted to have it like that, that would give you 30-hour battery lifetime. This is just an overview of the electrical system captured. Again, showing all the components I just described. And it just came out, this is the board without all the etching shown, just for clarity, and the actual board itself that's underneath the screen in the apparatus.
So like I mentioned earlier, we have the function where we can lock or unlock our actuators, and what that allows us to do is essentially not shut down the system, but disable the user from being able to move. You know, that can be used for things like if you wanted to type on a keyboard, you can angle your wrist up to a certain degree and lock it there. The other option, the other interface we have is turning on the backlight, as you can see here. Just so, you know, if it's at night, if you want to look at your screen, it'll make it easier to see. And then there's 2 more areas on the bottom where we got the U/D and L/R. That's just saying the up and down actuator and the left and right actuator. And when it's good, that means you're not carrying too heavy of a load. And if you are carrying too heavy of a load, it's going to tell you max load, and you can't see the LED on there, but that's going to turn red and the vibration mode is going to turn off. And so, so even though we're at a good spot with our project, we do have some other future work we want to work on. Mostly is getting fabric that ventilates better, because the fabric we have right now heats up pretty quickly. Also for the side actuator, as well, John just demonstrated, it's kind of slow. So we want to make that a little bit quicker and match human speed a little bit more.
The top one is fast, but the side one not so much.
Yeah, also probably look into using a faster writing controller, faster processing power overall. And since this for us is a proof of concept, we want to extend it out to other joints and limbs. And finally, just use better sensors, maybe for better reading, for better fitting. Questions?